Hello, good evening. Am I audible? Hello, good evening. Am I audible to you? Hello, good evening. Am I audible to you? Okay. So it is 6:30. Good evening to all. Let us start. Now we will be solving some numerical problems uh, based on whatever we have learned in the last two sessions. Okay. Let us directly go to the numerical problems. Okay. All of you can, if you want, you can copy the questions and you can solve it along with me. Okay. This is the first question. First, we will see some multiple choice questions. Okay. I think this question is seen by all of you. Are you able to see the question? Are you able to see my slide? Okay. I think you are able to see the slide. Okay. Now copy the, which of the following is not the property of an equipotential surface? Which of the following is not the property of an equipotential surface? That's a question. So let us go through them. The first one, they do not cross each other. We know that electric field lines will never cross each other. Two electric field lines will never cross each other. If it is a case, we know the electric field lines are the normals drawn to the equipotential surface. Electric field lines and equipotential surfaces will be normal to each other. So if two equipotential surfaces are intersecting like this, and their normals, if you draw one normal to this one, this is a normal drawn to this, and this is the normal drawn to this one. So these two electric field lines also will intersect. So what we can conclude from this, these equipotential surfaces can never cross. It is a property. The second one, the work done in carrying a charge from one point to another on an equipotential surface is 0. Actually, it is a property because all the points will be at the same potential. So if you just shift a charge from one point to another on the equipotential surface, no work is needed. Now, for a uniform electric field, they are concentric spheres. Actually, in the last class, you have seen how the equipotential surfaces are formed in the case of a uniform field. They are parallel planes. So this is not correct. So what about the next one? They can be imaginary spheres. Of course, equipotential surfaces can be imaginary spheres in the case of isolated point charges. So our answer is C. C is the answer. What is it? Equipotential surfaces for a uniform electric field, they are concentric spheres. That is the right answer. So to answer this, you should be aware of all the properties exhibited by equipotential surfaces. Now see this. An electric dipole is placed in an, one second. Are you able to read it? Or this taskbar is preventing you from reading? Now it will be okay. Okay. The equipotential surface, the electric dipole is placed in a uniform electric field of 10 raised to 5 Newton per Coulomb at an angle of 30 degree, experiences a torque equal to 4 meter. The charge on the dipole length 2 centimeter is. So what are the things given here? It is given the electric field is given. Electric field E is equal to I can't read it. Just a minute. Two into 10 raised to negative. 2 into 10 raised to 5. Electric field is 2 into 10 raised to 5. Okay. So electric field is equal to 2 into 10 to the power of 5 Newton per Coulomb. And it is making an angle of 30 degree. Theta is equal to 30 degree. And it experiences a torque. That's also given. It is 4 Newton meter. And you are asked to find the, and dipole length is also given. 2A is equal to 2 centimeter. That is, don't forget to convert it into meter. 2 into 10 raised to negative 2 meter. And you should find the charge, Q. So we should recall the equation for the torque. The magnitude of torque is given by P E sine theta. So torque is given. It is 4. And P is 2A into Q. And this is 2A into Q E sine theta. We can substitute the values. 2A is given. The length of the dipole is 2 into 10 raised to negative 6. Charge we have to find. And the electric field is also given 2 into 10 raised to 5 into sine 30. Yes, sine 30. So again, we can substitute it as 2 into 10 raised to negative 6 into Q into 2 into 10 raised to 5 into sine theta is 1 by 2. Sine theta is 1 by 2. So we can solve this and you can easily find the value of Q. Let me see anybody how posted the answer in the chat box. Anybody got the value of Q from this? What is the right answer? So again, we can write it as 4 is equal to, we have a 2 here and 1 by 2 here, we can cancel it. So 1, 2 remains there. 2 into 10 raised to negative 6 into Q into 10 raised to, sorry, this is 2 into 10 raised to negative centimeter, like negative 2. Or it is a, not negative 6, sorry, I made a mistake here. It is 10 raised to negative 2. 10 raised to negative 2. So this is 10 raised to negative 2 into 10 raised to 5. On simplification, you will get 4 is equal to 2 into 10 raised to 3 into Q. So Q is equal to 4 by 2 into 10 raised to 3. That will be 10 raised to 3. That is 2 into 10 raised to negative 3 Coulomb. But that answer is not there. But we have the answer 2 MC, millicoulomb. This is the answer. 2 millicoulomb. C is the answer. So it's a simple question actually. But you have to make a lot of substitutions. And we should know, to solve these questions, you should know the expression for the torque. You should know the expression for, not the expression for P. Even though it is a 1 mark question, you have to do a little calculation to get the answer. Don't blindly go and tick any answer. So complete all these things and you can find the answer. Now we will go to the next question. The electric field at a distance 3R by 2. 3R by 2. From the center of a charged conducting spherical shell is of radius R is E. So we have a charged spherical shell of radius R. And actually, it is given that the electric field at a point which is at a distance 3R by 2 from the center is E. So this is the point which is at a distance 3R by 2 from the center. 3R by 2 means it will be 3 by 2 is 1.5. Oh, it will be 1.5 R. Definitely, it will be outside the spherical shell. So outside the spherical shell at a point, at this much distance is given as E. And you were asked to find the electric field at a distance R by 2 from the center of the spherical shell. So what we can say a point somewhere here. The distance is R by 2. So how do you find the answer? Remember that it is a spherical shell. It's a tricky question. What will be the answer? Is it E by 2, 0, E by 3 or E? So we learned the properties of or the electric field due to a spherical shell as an application of Gauss theorem. We have seen that the electric field is existing outside the shell, but all the points inside the shell, the electric field is 0 because the entire charge is on the surface of this spherical shell. So inside the shell, the electric field will be 0. So what is this? The distance of the point from the center of the spherical shell is R by 2. That is half of radius. Obviously, the distance R by 2, that point will be inside the spherical shell. And the electric field will be 0. So our answer is this one. So it's a simple one. You must know only one thing. The electric field due to a spherical shell, inside it is 0. But they have given too many things. At a point 3R by 2, it is E. And how to find it inside. Only one thing in this case. Directly write R by 2 is definitely less than R. So that point will be inside. Directly write 0. No need of doing any calculation. Again. Okay. So this is a slightly different question. Two equal and opposite charges of masses m1 and m2 are accelerated in a uniform electric field through the same distance. What is the ratio of magnitudes of their acceleration if their masses are in the ratio 1:2? So we have two charges. They have masses m1 and m2, and we have to do a little bit of calculation. Okay, so let us see how to solve it. We know when a charge Q is there are two charges. One is positive Q. Let me call it as positive Q, and the other one is negative Q. And they are accelerated in the same uniform electric field. So both the forces will experience a force F. So this first one will experience a force positive QE, and the second one will experience a force negative QE. The choices are not given here. Actually, the four choices are there. So let us try. What will be the answer? This is positive QE and this is negative QE. Now, they have masses. The first one has a mass of M1 and the second one has a mass of M2. And you are asked to find the ratio of their magnitudes of their accelerations. So let us find the acceleration. What will be the acceleration of the first? And that we have to use a formula from the 11th class. F is equal to M into A. Force is equal to, just recall that formula, Newton's second law. F is equal to ma. So A will be equal to F by M. So we can say acceleration, the magnitude of acceleration of the first one will be QE divided by M1. And for the other one, acceleration A2 will be, I'm not writing the sign negative because it is very clearly mentioned that you have to find the ratio of the magnitude of the accelerations. So A2 will be QE divided by what it will be M2. Now we can easily find the ratio of A1 to A2. How to find the ratio of A1 to A2? A1 by A2 is equal to what it is? A1 is QE by M1. Sorry, M1. And A2 is QE by M2. QE and QE are common things. We can cancel them. And this will be 1 by M1 by 1 by M2, which is M2 divided by M1. But what is given to us? M1 by M1 is to M2 is given. M1 is to M2 is 1:2. But our answer is M2 is to M1. So what it will be? M1 is to M2 is 1:2. Definitely M2 is to M1 is 2:1. So answer is 2:1. So the ratio is simply when the masses are in the ratio 1:2, accelerations will be in the ratio 2:1, provided they are acted upon by the same force. So their accelerations will be in the ratio of the reciprocal of the ratio of this masses. M1 by M2 is 1/2. So M2 by M1 will be the ratio of accelerations. So keep it in your mind. You can directly write when you see 1:2, you will be able to write 2:1. But this is the theory behind behind this particular problem. Okay. Shall we go to the next? According to the Coulomb's law, which is the correct relation for the following figure? So it is you have to analyze this figure and you have to give the answer. You have to analyze the figure and find something, and you should find the correct choice from the given four choices. So what you can see, this is a charge Q1, this is a charge Q2. What actually Q1 is doing? Q1 is, both of them are attracting each other. So this is applying a force in that direction, this one is attracting a force in the, both are attracting each other. So from the figure, it is very clear that these arrows show that these two charges are attracting each other. And there's a very simple property. Similar charges or like charges will repel each other, and unlike charges will attract each other. So definitely what you can say about Q1 and Q2? Because they are attracting each other, one of them must be positive and the other one should be negative. So if I assume Q1 as positive, then Q2 should be negative. No problem. If I take Q2 as positive, Q1 will be negative. So what is Q1 into Q2? A positive number multiplied by a negative number. What will be the answer? Definitely, product of positive and negative numbers will be a negative number. So Q1, Q2 is negative. The same idea can be written like this, no problem. Negative means it should be less than 0. So go for the choice. Actually, negative answer is not given. The first choice give Q1, Q2 is greater than 0. Second choice says Q1 and Q2 are equal to, product is 0. Third one says Q1, Q2 is less than 0. So our answer is the third choice. That is Q1 into Q2 is less than 0. Okay. It's not very difficult, but after seeing this figure, you should be able to understand what type of forces are acting. So if these arrows are like this, what will be your answer? In case the question is like this, they have given two arrows like this. Q1 is moving in this direction and Q2 under the force is moving in the other direction. So what are they doing? Definitely they are repelling each other. The other case, it can be asked like that also. So these two Q1 and Q2 are repelling each other. What does it mean? What type of charges will repel each other? Like charges. So if Q1 is positive, Q2 is also positive. So their product will be positive. If Q1 is negative, Q2 is also negative. And their product will be positive. So answer will be definitely which option? Q1, Q2 is greater than 0, which is a positive number. Okay. Now we can go to the next question. I think it is clear. Okay, please make a note of the question. And I think I'm giving ample time for you to copy the question and you can also solve it. Don't wait for me to solve. If you get the answer, you can post it in the chat box. This is another one. The electric potential on the axis of an electric dipole at a distance r from its center is V. The electric potential on the axis of an electric dipole at a distance r from its center is V. So this is a dipole made up of two charges, positive Q and negative Q. And what it is given at a distance r from the center. Somebody have put the answer. We have a point P. And at this point, the potential will be V. So you are asked to find the potential at a point at the same distance on the equatorial line. So this is the point next one, or let me name it as capital R. What will be the potential at this point, which is at a distance R from the center? Sometimes you may commit a mistake. You will write V by 2 suddenly because we have seen that is about the electric field. For a short dipole, electric field, if it is E, it will be E by 2 here. But it is not electric field. It is about the potential. What is the potential at a point on the equatorial line? At all points on the equatorial line, the potential will be 0. We have proved it in the morning session. Okay. Let us see what the answer is given. Option 3 is given by somebody. Why they have given option 3? They thought that it is electric field. Actually, it is not electric field, electric potential. The potential at all points on the equatorial line is 0. So our answer is 0. No need of any calculation. It is very clearly mentioned that the point is on the equatorial line. All the points on the equatorial line will have 0 potential. So our answer is 0. Okay. Make that correction. Now we will go to the next. This is slightly difficult one. A charge Q is placed at the center of the line joining two equal charges, positive Q. The system of three charges are in equilibrium if Q is equal to. Okay, how to solve it? You can also start solving it. We have 2 points. So I have a charge Q here, another charge Q here. Then at the center of the line joining these two charges, Q and capital Q. They are capital Q. At the center, another charge Q is kept. And what we want is these three charges, the system of these three charges must be in equilibrium. Definitely Q will be in equilibrium. Why? The center one, Q will be in equilibrium. What is the reason? These are two equal charges. And the distance, the Q is located at the center of the line joining the two charges. So if this distance is R, this also will be R. Okay, let us see all the three charges are having the same. Q and capital Q have the equal charges. So if it is positive, this one also will be positive. And if both of them will apply the same force, same magnitude of force on Q, because the force is given by 1 by 4 pi epsilon 0 Q1 Q2 by R square. All the conditions are same for both the charges. Here it will be 1 by 4 pi epsilon 0 Q into capital Q by R square. And for this one, it will be 1 by 4 pi epsilon 0 into Q into capital Q by R square. Both will have the magnitude same. So if it is positive, this one is also positive. And if we consider these three as positive charges, then it will be repelling in this direction. The first one will be repelling this small q in this direction, and this capital Q will be repelling it in the opposite direction with the same force. So these two forces acting on the small q will balance each other. So it will not experience any force. So this is in equilibrium. But that is not the only condition required for the equilibrium of all the three charges. These two also must be in equilibrium. So the resultant force acting on capital Q must be 0. And this capital Q also must be 0. So let us see how it is possible. So let me see this one. Here also all the conditions are same because it is a symmetric distribution. So let me find what is the force acting on this charge Q. This one I am taking. So there will be two forces acting on it. This one will be applying a force on this capital Q. And this one also will be applying a force on capital Q. And this should balance each other. So let us see what is the total force. 1 by 4 pi epsilon 0 capital Q into small q divided by R square. This distance is R square. I don't know the signs of this small q. So simply I wrote 1 by 4 pi epsilon 0 q into q divided by R square plus the next force is they are vectors. So I'm adding them. 1 by 4 pi epsilon 0. What will be the other force? This is capital Q. And this one is also capital Q. So what is the force expressed by it? Q into Q by, what is the distance between them? So this distance is R. This distance is R. This distance is again R. So the total distance will be R plus R. And it will be 2R. So what is the square of 2R? 2R the whole square. So this should be 0. The sum of these two forces must be 0 to get the resultant force as 0. So I can say 1 by 4 pi epsilon 0 q by small r square must be equal to, I am transforming this term to the next side, left side. Sorry, to the right side. So it will be minus or negative 1 by 4 pi epsilon 0 q into capital Q is q square divided by square of 2r. It will be 4r square. Square of 2r is 4r square. So we have some common terms on both sides. So let me cancel them. What are they? So when you solve this problem, no need to write this 1 by 4 pi epsilon 0 all. Simply you can write k and solve. So these two will be cancelling each other. 1q and q square. I can cancel. This r square and this r square will cancel. So we have the answer with us. What is the answer? Q is equal to, negative sign is there, capital Q is there, and by 4 is there. So what should be the value of small q to happen this? Again, we can check it with this charge also. Then if you substitute this as negative q by 4, and if you find the total force on this capital Q again, definitely it will be also equal to 0. There will not be any change. You can check it. If you want, you can have a check on it. So what is our answer? We have 4 options. negative q by 2, negative q by 4, positive q by 4, and positive q by 2. Which is the answer? We already got it. This value of small q should be negative q by 4 for the system to be in equilibrium. So we must know about equilibrium. Then we must know Coulomb's law. Then we can easily solve this problem. Okay. Anybody posted the answer? Okay. Some option 3, maybe for the last question. So the option is, here it is, option B, negative q divided by 4. Okay. Now we will move to the next question. All these are multiple choice questions first. Okay. A particle of mass m and charge negative q is moving with a uniform speed v in a circle of radius r, with another charge small q at the center of the circle. The value of r. What should be the radius of that circle? Okay, this also something we have to recall from our 11th class syllabus. So this is a circular path. Imagine that this is a circular path. So we have a charge at the center. That is q, positive q. And another charge, it is negative q of mass m. Its mass is m. And it was moving around in a circle around this charge positive q with a constant velocity, with a constant speed of v, not velocity, constant speed v. Okay. Which equation we need from our 11th class? This is an example of a circular motion. So a circular motion always require a force which is acting towards the center of the circular path, which is called the centripetal force. Here the centripetal force is supplied by the electrostatic force of attraction between this positive q charge and the negative q charge. So this positive q will be attracting it towards its center. So this will provide the centripetal force. So that centripetal force is given by 1 by 4 pi epsilon 0 q into q. I'm considering only the magnitude again, by r square. Q cube by r square. This will be the centripetal force. And again, we know the expression for the centripetal force. What is the expression for the centripetal force? When an object of mass m, when it moves with a velocity v in a circle of radius r, the required centripetal force is given by mv square by r. So this is equal to mv square by r. Now we can equate these two and you can find the value of the radius r. Equate these two and do some simple mathematical calculations and find the value of r. Can you complete it and find the answer? Okay, you can also do it. This can be written as 1 by, we can equate these two forces. So 1 by 4 pi epsilon 0 square by r square is equal to m v square by r. Again, these two will cancel. So we have q square in the numerator, 4 pi epsilon 0 into r in the denominator, and a v square. So from which we can find the value of r. R will be equal to q square divided by 4 pi epsilon 0 r. 4 pi epsilon 0 r. We were asked to find the value of r. Sorry, I will. Yeah, this will for q square is equal r is equal to, here we have the 4 pi epsilon 0 r into mv square is equal to q square. So this is equal to 4 pi epsilon 0 into mv square. So r will be 1 by 4 pi epsilon 0
Please
into.
switch off all other mics. Please switch off all other
We have
mics.
an m here, and we can write this q square by v square as q by v the whole square. So this is the answer. Let us see the choices. First one is 1 by 4 pi epsilon 0 q by v. This one is 1 by 4 pi epsilon 0 m into q by v the whole square. I think that is the answer. Right. R is equal to 1 by 4 pi epsilon 0 m into q by v the whole square. So our answer is option B. Very good. I got the answer from one school. Very good. The answer is correct. The answer is this option B. Okay. Now we can go to the next. Okay. Now we will move to the assertion recent questions. I have brought some assertion recent questions. Some 5 questions are there based on whatever we have learned. The first one is, an electron has a higher potential energy when it is at a location associated with a negative value of potential and has a lower potential energy when at a location associated with a positive potential. That is the assertion. The reason is, electrons move from a region of higher potential to a region of lower potential. So let us try to understand what is given in the assertion part. Sorry. An electron has a higher potential energy when it is at a location associated with a negative value of potential. Let us simply take example of 2 points A and B. Let me say the potential at this point is negative 10 volt and here it is positive 10 volt. Simply I'm saying the potential of A is negative 10 volt and potential of B is positive 10 volt. Now, if I keep an electron here at this A and another electron at E, let us find the potential energy. What will be the potential energy of the electron? If you know the potential and charge, the energy is given by Q into V. Potential energy will be Q into V. Q is the charge and V is the potential of the point where it is kept. So what is E? The charge of electron is negative E. So Q is negative E and potential here is negative 10. So what is the potential energy? It will be 10E. The sign will be positive. It has this much joule of energy. Now let us see what happens here. Again, the same electron, it is kept at a point where the potential is positive. So associated with this electron, we have a positive potential. Okay, you can find the potential energy of this electron also. It will be negative E again, negative E into 10. So it is negative 10 electron volt. So, negative 10 E joule. So which is greater, positive 10E or negative 10E? Which energy is more? Definitely positive 10E is more than negative 10E. So what the statement given here? An electron has a higher potential energy when it is at a location associated with a negative value of potential and has a lower potential energy when it is at a location associated with a positive potential. Definitely, when it was at this negative potential location, it has an energy of 10E. But when it is at a positive potential, it has an energy only negative 10E. Definitely, at this point, the electron has more energy. So what does it say? This assertion is correct. Our assertion is correct. When electron is at a negative potential background, it has more energy. Now, what about the reason? The reason gives the electron move from a region of higher potential to a region of lower potential. Okay, when this electron has negative 10 electron volt, negative 10 E energy, and when it has negative 10 E energy here. Normally, if I keep an electron here, will it move towards this A or move towards B? What do you say? An electron has a negative charge. This is at a negative potential, so definitely electron will not move from here to here. This electron will experience a repulsive force from here. So this is not correct. Electron will move from a lower potential to a higher potential. So here it is given us, it will move from a higher potential to a region of lower potential. So our answer is, what are the things given here? The things given are the assertion. The first answer is A. If assertion is true, if assertion and reason are true, and reason is the correct explanation of A. The answer will be B. If assertion and reason are true, but reason is not the correct explanation of okay, it doesn't matter. In this case, we can directly say our assertion is true, but our reason is false. So we can go for the choices A, B, C, D, where it is given. Assertion is right, and assertion is true, and reason is false. So our answer is assertion A is true, and reason is false. Okay, so we have to think a lot of things to answer a simple assertion reason question. That's why it is called a competency based question. You have to think a lot of things, incorporate a lot of things to answer these type of questions. Most of the students, what they are doing is they will just write either A, B, C, or D, but just try to connect these things with the theory which we have learned in the classes. Analyze it, and you will be able to find the right answer. Now, next one. If Gaussian surface does not enclose any charge, then flux through the surface is zero. That is the assertion. If Gaussian surface does not enclose any charge, then flux through the surface is zero. This is what Gauss theorem says. When there is no charge is enclosed by the Gaussian surface, the flux passing through it will be zero. No doubt. The direct statement of directly we can deduce this from the Gauss theorem. So what do you say? Whether it is true or false? This is true. Now, if Gaussian surface does not enclose any charge, then E at any point on the Gaussian surface must be zero. If there is no charge on the Gaussian surface, then the electric field at any point on the Gaussian surface must be zero. Is it true? So if you have some other charges outside it, if you have a positive charge Q, there is no charge inside the Gaussian surface, but we have a positive charge Q outside it, which is at a distance R from the Gaussian surface. So definitely at this point, this positive charge will produce an electric field where this Gaussian surface is located. So if there are some other charges in the vicinity of this Gaussian surface, on the surface, we can have an electric field. It is not compulsory that if there is no charge inside, the electric field must be zero here. So our reason is not exactly correct. It doesn't say anything about the charges outside the Gaussian surface. If there are some charges outside the Gaussian surface, only one condition is given here. The charges are, no charge is enclosed by the Gaussian surface. But it doesn't mean that there is no charge in the surrounding region. If there are some charges in the surroundings, definitely there will be electric field at the surface. So in this case also, we can say the assertion is true, but the reason is false. The answer is assertion is true, reason is false. Okay. Let us go to the next question. If a point charge be revolved in a circle around another charge as the center of circle, then work done by electric field will be zero. This case we have seen earlier. So we have, what's the situation? There's a circular path, a charge at the center, another charge is taken once around this circle. It says that work done is equal to zero for that. Do you agree? Two cases we can say, because it is all those points will be or that circular path at all the points potential will be same. So it's an equipotential surface, no work is needed, or it is coming back to the initial position, its displacement is zero, and work is the dot product of force and displacement. Work done is the dot product of force and displacement. F dot S will be definitely zero if S is zero. So what is the answer given here? Work done is equal to dot product of force and displacement. So when displacement is zero, definitely work done is also zero. So what is our answer? What is our answer? Assertion is true, reason is also true, and this is the correct explanation. Reason is the correct explanation of assertion. Here displacement S is equal to zero, and work done is the dot product of force and displacement. When displacement is 0, dot product of a vector and 0 vector will be definitely 0. So both are correct. And it is a correct explanation of, the reason is the correct explanation of assertion. Okay. Now we will move to the next question. Electrostatic field lines can never be closed loops. Electrostatic field lines can never be closed loops. Reason? What do you say about this one? Assertion? Is it possible? It is not possible. That is one of the most important property of our electric field line. Electric field can be never closed loops. So let us think of the reason. What is the reason? We learned that electric field lines will start from a positive charge and they should end in a negative charge. If it is in the form of a closed loop, we must have the same positive. We must have a positive charge and negative charge at the same location, which is impossible. We can't keep two charges at the same point at the same time. So that is the reason. But what is the reason given here? The number of electric lines of force originating or terminating on a charge is proportional to the magnitude of the charge. If we have a large number of electric field lines going towards a particular body or a particular surface, or if there are large number of electric field lines moving away from a particular surface, what does it indicate? So there is a property of electric field lines. In a very strong electric field lines are crowded, and in a very weak electric field lines are separated by a large distance. The distance between the electric field lines are very large. So the relative closeness or degree of closeness of field lines will give you an idea about how strong is the field. Again, we know the expression for the electric field. Electric field is 1 by 4 pi epsilon 0 q by r square. Electric field due to a point charge. 1 by 4 pi epsilon 0 q by r square. So this electric field at a certain point, the distance is fixed. Now the electric field strength is determined by the charge. 1 by 4 pi epsilon 0 q by r square. It is directly proportional to q and inversely proportional to r square. It is directly proportional to q and inversely proportional to r square. So if q is more, electric field will be stronger. That means more number of lines will be present there. So this reason is correct, but assertion is correct. Reason is also correct, but this reason is not the correct explanation of why electric field lines are not in the form of closed loops. So what is our conclusion? Both assertion and reason are correct, but it is not the correct explanation of the reason is not the correct explanation of assertion. Okay. This is almost this is somewhat simple compared to other questions. Now, one more. When we produce charge Q1 on a body by rubbing it against another body which gets a charge Q2 in the process, then Q1 plus Q2 must be 0. Think of it. Just I am rubbing one object with another. For example, I am rubbing ebonite with wool. Ebonite is rubbed with wool. What will happen? We know ebonite will become negatively charged. Why? Some electrons are shifted from ebonite to the wool. So as a system, if you consider both ebonite and wool as a system, so some electrons are transferred from transferred from wool to ebonite. Wool is becoming positive and ebonite is becoming negative. Ebonite gains electrons, so it becomes negative, and wool loses electrons, so it becomes positive. So it is taking place if it is taking place in an isolated system, we are considering only these two objects. Because of rubbing, some electrons are transferred from wool to ebonite. So if ebonite gets negative Q charge, then the charge occurred by the wool must be negative Q. Why? Because wool is donating that electrons. So those entire electrons are absorbed by the ebonite. So both of them will be charged with equal magnitudes, but opposite charges. Ebonite is negative. If it has negative Q charge, wool will have positive Q charge. So what is the sum of these two? Positive Q and negative Q. What will be the sum? The sum will be definitely 0. So this statement is absolutely correct. So it directly says the electrons lost by the ebonite is gained by the ebonite. Electron lost by the wool, the electron lost by the wool is gained by the ebonite. So why it happens? No charge is missing, no charge is destroyed, or no charge is created in that system. Only the transfer of charges has taken place from one object to the other object. So definitely it is nothing but the law of conservation of charge. On an isolated system, the total charge remains constant. So this is correct. Assertion is correct. Reason is also correct. And it is the correct explanation of the assertion. So our choice will be definitely A. Okay. Okay. This much only. I have only 5 assertion reason questions I have already taken. Now we will move to some numerical problems which require a little skill to calculate it. So this is a question we have. You can see all these points A, B, C, D, and R. So now I will read the question. You can also read it. Charges positive Q and negative Q are placed at points A and B respectively. So we have 2 charges. One is positive, another one is negative. Where is positive Q charge located? Positive Q charge is located at A. And where is negative Q charge located? It is located at B. Now, this A and B are 2L apart. That means distance between A and B is 2L. A and B are separated by a distance of 2L. And it is mentioned then C is the midpoint between A and B. So this C is the midpoint of A and B. What you can conclude from this? AC is equal to CB. When total length AB is 2L, AC is L and CB is also L. So this much we can mark in this question after reading the first sentence. Positive charge is located at Q. Positive Q charge is located at A. Negative Q charge is located at B. And the C is the midpoint of AB. And A and B are 2L apart. Since C is the midpoint, AC is equal to L. CB is also equal to L. Now, it is given that B is the center of this semicircle. B is the center of the semicircle. So, what is BD? This is the diameter. BC is equal to L. So, definitely BD also must be L. Now, what we have to calculate? This is the situation. So, distance between A and C is L. This we have to analyze the question and we have to mark all those things in the figure. So, AC is L, CB is L, BD is L. Half of our work is over. Now, what they have asked? What is the work done in moving a charge positive Q along the semicircle CRD? So, I am moving a positive charge from which point? This point C. Along the semicircular path, I will reach R. Then I will go to T. You have to calculate what is the work done for that. Don't think that this is an equipotential surface. Why? Because there is a charge negative Q here, there is a charge positive Q here. If you consider even though the distance between all the points on the arc and B remains same, but this Q is at a different distance from different points on this arc. So this is this much distance. When you come to this point, positive Q is at a larger distance. When you come to this point, again, it is at a larger distance. When you come to this point, this distance is again increasing. When you come to this point, this distance is again increasing. So potential will not be same everywhere throughout CRB. Don't think like that. And after seeing this, you should say C and D are having same potential. So the work done is 0. Don't conclude like that. And so it's a tricky question. Now, how to find the work done in shifting a charge from C to D? We know that electrostatic field is a conservative field. So what does it mean? Today we have seen the work done is independent of the path. It depends only on the initial position and the final position. So the work done depends only on two things, the initial position and the final position. That is, the work done, even though it is displaced through this path, the displacement is only CD, that is 2L. Okay, C and D are 2 points in an electrostatic field. So we can find the work done to move a charge from C to D. Or if you are moving a unit positive charge from C to D, that will be the potential difference between D and C. So if the work done to move a unit positive charge from C to D, if I am moving a unit positive charge, then work done will be the potential difference between C and D. But if I move a charge capital Q, instead of unit positive charge, if I move a charge capital Q from C to D, then the work done will be a Q into potential difference between C and D. So what we have to find actually? In this problem, we have to find the potential difference between C and D. So how to find it? We can find the potential of C and we can find the potential of D. Then we can find potential of D minus potential of C. So we will get the potential difference. So let us try for that. So let us find the potential at C, VC. So there are two contributors. Positive Q will create a potential here. Negative Q at B also will create a potential at C. So let us calculate what it will be. 1 by 4 pi epsilon 0 positive Q by L. That will be the potential at C due to this positive charge. Plus, we can directly add potentials because they are not vectors. Remember that. So we have a charge negative Q, which is also at a distance L from C. So the potential at that point will be 1 by 4 pi epsilon 0 negative Q divided by L. So this is the distance L. So when you add this, what happens? 1 by 4 pi epsilon 0 we have here. The same 1 by 4 pi epsilon 0 we have on the other side. Here we have L, we have L. Here we have positive Q, here we have negative Q. So when these negative signs come here, both are equal, but this is positive, this is negative. Magnitudes are equal, but one is positive, one is negative. So definitely they will add to give 0. So what you can say about the point C, VC is at a 0 potential. Okay. Now let us try to find the potential of D. Potential at the point D. Okay, let us see whether it is 0. Then our work will be very easier. We can say potential work done is equal to 0. Directly we can say. So let us check. What is the potential at the point D due to the positive charge Q? Again, I'm going to the same formula. 1 by 4 pi epsilon 0. This is positive Q. Into I'm finding the potential at D. So into 1. I'm no need to write it. Q divided by. So what is the distance between A and D? This is L. This is L. This is also L. So what is the total distance between A and D? L plus L plus L. What it will be? 3L. No doubt it will be 3L. Plus, again, we have a negative charge where at B. So it also will produce a potential at D. That is equal to 1 by 4 pi epsilon 0 negative Q unit potential negative Q divided by what's the distance between B and D? It is L. Now we have to add these two. So we can add by using a little mathematics. So Q and L we have here. And here we have 1 by 3. Here we have minus 1 has gone, for pi epsilon 0 has gone, Q has gone, L has gone. So we have a minus 1. So this into 1 by 3 minus 1. What it is? 1 by 4 pi epsilon 0 Q by L into 1 minus 3 divided by 3. So it is equal to 1 by 4 pi epsilon 0 into Q by L into 1 minus 3 is negative 2 and this one is 3. And we can cancel these two and it becomes 1 by this 4 and 2 cancels to give 2 and 2 into 3 is 6. with a negative sign. 6 pi epsilon 0 into 2, no, not 2, sorry, q. This is the expression. Negative 1 by 6 pi epsilon 0 into q. This is the answer. Now, we got the potential of C and potential of D. So, what is the potential? VD minus VC. Potential difference between D and C will be VD minus VC. That's equal to VD is negative. I'm writing it as negative Q by 6 pi epsilon 0. And I forgot to write this L. Sorry. This L is there. 1 by negative Q by 4 pi epsilon 0 into L minus 0. No need to write it. Minus 0 will be this one. Now, how to find this is only the potential difference between C and D, not the work done. Yeah, thank you. Somebody was reminding me I missed L. Thank you. I have seen it. Thank you very much. So, VD minus VC will be equal to a negative Q by 6 pi epsilon 0 into L. This is a potential difference, but what we want to find, our aim is not the potential difference. Our ultimate aim is to find the work done. So work done is equal to, again, the charge which was shifted is capital Q, and potential difference between that one we got, it is equal to negative Q by 6 pi epsilon 0 L. So this will negative Q by 6 pi epsilon 0 L. This is the answer. This is the work done in moving a charge Q from C to D through R. It doesn't matter, even if we are taking it through this point in this way, or if you move it from in this direction or in this route, whatever route, whichever route we prefer between C and D, always work will be same, because the electric field is a conservative field. So I think it will be clear to you. So it's not very difficult, but you have to analyze the figure. We have to plan our answer in such a way that we can finally arrive at the answer. So aim, we should know what is work done. Work should be charge into potential difference. So we should know how to find the potential difference between 2 points in this case. Find the potential at D, find the potential at C, find the difference. That will be the potential difference. Then it should be multiplied with the charge. So final answer is this one. Okay. Another question. We have two capacitors. Actually, I could not finish all those portions, but you know know about capacitors. Energy of a charged capacitor, the general expression is what it is? Half C V square, where C is the capacitance and V is the energy. If C and V are given, expression is half C V square. Now, another important equation whose derivation is actually not in the syllabus. If you have a capacitor which is charged to a potential V1, and if it is connected across another capacitor C2, which is charged to a potential V2. So we have two capacitors, one having a capacitance C1, and it is charged to a potential V1. And second capacitor, it has a capacitance of C2, and it is charged to a potential V2. When they connect these two together, then there will be a common potential developed across these two. And that common potential is given by C1 V1 plus, you just note down this equation, divided by C1 plus C2. This is the expression for the common potential when two capacitors of capacitances C1 and C2 charged to potentials V1 and V2 when they are connected together in this way. So common potential will be C1 V1 plus C2 V2 divided by C1 plus C2. So these two equations are needed to solve this equation. Since I could not finish that in the morning sessions and afternoon session, so I have given these two equations. Capacitors are not difficult. It is a really easy topic. You can learn it. Now, let us see what is the question. Now we can go to the question. This is your previous knowledge to solve this question. A capacitor of capacity C1 is charged to the potential of V0. Okay, we have a capacitance C1. It is charged to a potential C0, our C1. In our equation, C1 is C1 itself, but V1 is written as V0. It is fully charged. and disconnected it from the battery. It is disconnected from the battery. It is connected with an uncharged capacitor of capacity C2. The second capacitor has a capacitance of C2, but it is not charged. That means both the plates are not having any charge on it. So what will be the potential across its plate? If it is an uncharged one, definitely V2 will be equal to 0. Always remember that if it is an uncharged capacitor, the meaning is there is no charges on the plates of the capacitor. So the PD across the plates will be 0. That is the second capacitor C2. It is uncharged. So they have connected like this, and there is a key here. Now, what we are going to do is I'm going to close this key. I'm going to close this key. And what you have to do is, when I close this key, you should find the ratio of the energies in this connection before the switch is closed to the energy of the capacitor after the switch is closed. So two situations are given. One, the switch is, the switch is open. Before closing that switch, it is already open. The figure, it is given like that. So you have to find the energy of this capacitors before closing this switch. Then when you close this switch, what happens there? And again, you have to find the energy of the capacitors, two capacitors together after closing this switch. Then you should find the ratio of energy before to the energy after the switch is applied or switched on. This is the question. So we need this expression because C and V are given. So we can find the energy using this relation. Energy is equal to half CV square. So let us see what will happen before this switch is closed. So this is an open circuit. Charges cannot flow from one place to another. So the second capacitor C2 is uncharged. So there is energy. We have charges only in the first capacitor. It has a capacitance of C1 and its potential difference between the plates is V0. So before closing the switch, let me call it initial or before VI. So energy before closing this switch. So let me call it as EI, energy initially. Definitely half, expression is half is CV square, but C is C1, V is V0. So we can write C1 into V0 square. Okay. Plus, what is the energy on this capacitor before it is closed? Definitely, there is no potential difference across the plates. It is 0. So half CV square, half C into 0 square, it is 0. So this is the only energy in this, or electrostatic energy stored in this situation. Now, when we close this switch, what happens? So now circuit is closed, charges can be shared between, and this situation arises there. Two capacitors are connected together. So we know the expression for the common potential. The charges will be moving from this first capacitor to the second capacitor, and a common potential is created there, and charges are shared between the two. So this one also will be charged. Now we can find the common potential of this combination. Now it will be C1 into V1 is V0. Don't forget it. It is written as V0 plus C2. What is V2? It is 0. It was an uncharged one in the beginning, divided by C1 plus C2. So the common potential will be C1 V0 divided by C1 plus C2. Now, what type of a combination is this? These two plates are connected together, and these two plates are also connected together. So both the plates are connected to common points. So is it a parallel combination or a series combination? Definitely this is a series parallel combination of two capacitors, and the total capacitance of this system after closing the key will be C1 plus C2. Now we have a capacitor. This circuit is equivalent to a single capacitor of capacitance C1 plus C2, and the PD across the plates is C1 into V0 divided by C1 plus C2. That is what is called effective capacitance. These two capacitors will together behave like a single capacitor, whose capacitance is C1 plus C2, and the potential across the plates is C1 V0 by C1 plus C2. So we can calculate the energy, the final energy. It will be again half what we have in the place of C1. So this system has two capacitors and they are connected in in parallel. So it will be C1 plus C2. And what is V? The common potential is C1 V0 divided by C1 plus C2. So we have to square it. So what will happen here? C1 square, V0 square, that is C1 square, V0 square divided by C1 plus C2 the whole square. C1 plus C2 the whole square. So this we can simplify. There are some shortcut equations, but this is the way how to solve it. Now we can cancel certain terms. This C1 plus C2 and this square will be cancelling. And what we have, this is equal to half of, we have a C1 square in the numerator, V0 square in the numerator, divided by the denominator we have C1 plus C2. Now we can find the ratio of EI, whatever it may be. What was asked, find the ratio of the energies before and after the connection. So EI divided by EF is equal to what it will be. EI is half C1 V0 square divided by half C1 square V0 square, the whole divided by C1 plus C2. So what we have, V0 square, V0 square cancels, C1 and C1 square cancel, half and half will cancel. So what will happen here? C1 plus C2 will go to the numerator, and we have the C1 in the denominator. So the ratio of energies will be C1 plus C2 divided by C1. So now you can keep this one as an equation like this. If it is asked for a 1 mark question, definitely directly you can write the ratio, sum of the capacitors divided by the capacitance of the first capacitor, C1 plus C2 divided by C1. This is how to solve this question. Okay. Now we will move to the next question. Okay. So it's a little lengthy and not these two equations. If you are not able to solve along with me, so you can solve it later. Remember these two equations and remember all the steps. You will be able to solve it. It is not a difficult question. And I don't know what is the reason. These type of questions they are asking almost every year. These two capacitors, sometimes it is uncharged. And the question will be in a slightly different way. Sometimes they will ask, what is the energy lost in this process? What is the energy lost in this process when you connect two capacitors like this? So what you have to do, you know the initial energy is this much and you know the final energy is this much. So how to find the energy loss? You just subtract EF, EI, find the difference between EI and EF. So if EI minus EF is, you are getting some value, even if initial energy is greater than the final energy. Definitely some energy is lost in some other forms. So if there is a difference between EI and EF, that much energy will be lost in this process. Instead of finding the ratio of energies, this question can be to find the energy lost during this process. For that, what you have to do is you should just find EI minus EF. Definitely, it will be a positive quantity and energy is lost. And what are the possible causes for this energy loss? That also can be asked. What are the possible reasons or why energy is lost in this process? And we know when we connect these two together, charges will be moving from through these wires. There will be movement of charges through these wires. So when charges move through a wire, there will be a momentary current. A small current will be there. Even though we use copper, thick copper wires to connect them together, the thick copper wire also has got some resistance. So when charges move through a resistor, energy is lost in the form of heat. Joule's law of heating, you are going to learn tomorrow. You have already learned it, I square RT. So that much energy will be lost in this wires when electrons are moving through these wires. One more thing, when electrons will move, they will be, initially they are at rest. When they start moving, they are accelerated motion. The charge, electrons will start, initially they were at rest, then suddenly they will begin to move. So that process is an accelerated process. Electrons are accelerated. So accelerated motion of charges will always produce a particular type of waves in the surrounding region. What are they called? You are learning about those waves. They are called electromagnetic waves. When charges are accelerated, electromagnetic waves are generated. So because of that, some electromagnetic waves are also generated in the surroundings. So these are the two possible ways of loss of energy when we connect capacitors together. One in the form of heat, because of the movement of electrons through the wire, and the movement of the accelerated movement of the electrons through the wire can produce electromagnetic waves. So that also will carry some energy. So that is why the initial energy will be always greater than the final energy, or final energy will be always less than the initial energy. Okay, this question can be asked in that way. Definitely, almost every year you can expect such a question. Every year we are seeing it in the question paper. So connecting capacitors together. Okay, now we will move to the next question. Two large thin metal plates are parallel and close to each other. On their inner faces, the plates have surface charge densities of opposite signs and of magnitude 17.7 into 10 raised to negative 22 Coulomb per meter square. What is the electric field intensity E in the outer region of the first plate and between the plates? Okay, let us say these are the two plates. Both of them are having charges with the surface densities. Let me say this is, we have positive sigma here, positive sigma, and this has negative sigma, inner regions, positive sigma and negative sigma. So sigma is given as 17.7 into 10 raised to negative 22 Coulomb per meter square. And here it is negative 17.7 into 10 raised to negative 22 Coulomb per meter square. And you are asked to find the electric field intensity in the outer region of the first plate. This is the first plate. This is the second plate. You are asked to find the electric field at this point. This I have explained in the morning class. What is the, if these two charges, these two plates have equal and opposite charges with the same surface density, the electric field in the region between them will be sigma by epsilon 0, and here it will be 0. Here also it will be 0. It will be a direct question, direct substitution. No need to do any calculations. We can, of course, we can do, because sigma is given and we know the value of epsilon 0. So the electric field inside the plates will be sigma by epsilon 0, and outer regions will have actually 0 electric field. So sigma is given and we know the value of epsilon 0, 8.857 into this one. So directly substitute the values of sigma and epsilon 0 and find the electric field in between the plates. What is this situation called? Two plates having equal charge densities. One is positively charged and another one is negatively charged. This is actually a capacitor, a parallel plate capacitor. So the electric field is confined to the region between the two plates. So it's a simple question, relatively simple one, but only you have to identify this situation as a capacitor, and the electric field will be 0 outside and it will be sigma by epsilon 0 inside. Okay, I'm not going to solve it. Okay, now let us see this question. In a parallel plate capacitor with air between the plates, each plate has each plate has an area of 6 into 10 raised to negative 3 meters square. And the separation between the plates is 3 millimeter. Calculate the capacitance of the capacitor. The first part is very simple. Direct substitution. We have 3 charges. Oh, sorry. Okay. It's a parallel plate capacitor with the area has given A is equal to 6 into 10 raised to negative 3 meter. The separation between the plates is 3 millimeter. That is D is equal to 3 into 10 raised to negative 3. This is meter square. 10 raised to negative 3 meter. So A and D are given, and you were asked to find the capacitance. So C will be equal to what it will be? Epsilon 0 A by D. The first part is direct substitution, and you can solve it. I'm not going to solve this because just a mere substitution of this A, D, and epsilon 0. So you will be able to find the capacitance. Now, what is the second question? If this capacitor is connected to a 100-volt supply, what would be the charge on each plate? We know the relation between. Once we got the capacitance C will be, we know the value of C, and Q is also given, V is also given. So we know the relation between C, Q, and VC is equal to Q by V. So we can find it. By using the relation between C, Q, and V, you will be able to find the charge on the plate. So directly, it is also a direct question. But the next part requires little explanation. So here we have, it is directly given what much potential is applied there, and you will be able to find the charge on each plate. It's a direct question. These two are direct questions, so no need to worry about it. All of you will be able to solve it. Direct writing the equation and substitute. Now let us see what will happen to the third part. So in the third part, we are introducing a mica sheet. Mica sheet is a dielectric, and its dielectric constant is 6, and whose thickness is between the plates, the thickness is 3 millimeter. We know the distance between the plates is also 3 millimeter. So we are introducing a mica sheet of the same thickness in between the two plates. So what will happen to the new capacitors? Let me call it a C dash. C dash will be equal to K into C. You know the relation. When a dielectric is used to fully fill the region between the two plates, the capacitance will become K times. So K dash will be equal to K into C. So definitely, since K is 6, so the new capacitance will be 6 times. 6 into C. So C dash will be 6C. Now what happens? We are not removing the V. The same source is connected there. The 100-volt source is connected there. So that will keep the potential difference between the plates always at 100 volt. So we are not disconnecting this battery. That is the importance here. So whenever a battery is connected to a capacitor, the PD across the plates of this capacitor will be equal to the terminal voltage 100, the voltage given by this battery. That will be 100 volt. Always it will be 100, but the capacitance has increased by 6 times. But potential remains constant. So what will happen to the charge on the plate? Or how it will affect? How it will be affected? Potential difference remains same, but capacitance has increased. At the same potential, the capacitance has increased. So how it is possible? So when the potential remains same, when the capacitance has increased, this system will be able to store more charges. So when keeping the voltage constant, that is the basic principle of the capacitor. I have explained it in the afternoon class with the 2 plates. How we can make more charges to store in a plate. So by increasing the capacitance of this capacitor, we are able to store more charges on this capacitor. So when the battery is connected here, the potential difference across the plates remains same, and more charges, 6 times charges will be stored in this capacitor. So that is the how would charge on the plate be affected when this dielectric inserted while the capacitor is connected to the battery. The situation is different when this battery is not connected here. So that also I will mention here. So when the battery is connected, the PD across the plates remains same. When the capacitance increases, the charging capacity also will increase. This capacitor will draw more charges from the battery and it will be stored in the capacitor. Now, let us think of the case. This battery is disconnected. Once it is charged to 100 volt, then a dielectric slab is introduced in between the plates. How it will affect this capacitor? So when the battery is removed, the charges on the plates will remain same. There should not, we can't increase the charges on the plates because there is no external source to supply the charges to the capacitors. So actually what the dielectric will do here, the dielectric will reduce the electric field between the plates by a process which is called polarization. So the PD across the plates will decrease. So the PD across the plates will decrease and the capacitance will increase. So that cases are different. When the battery is connected, the potential difference across the plates will remain same, but the capacitor will store more charges. Is it clear? When this capacitor is connected to an external battery, and if you introduce a dielectric in between the plates, PD across the plates will remain same, and the capacitor will store more charges. But when once it is charged and disconnected, and if you introduce a dielectric slab in between, this dielectric slab will reduce the potential difference between the plates and the capacitance will increase. This is the mechanism to increase the capacitance in 2 different cases. I think we have time to solve one more question. Okay, shall I go for it? With your permission, I think some 5 minutes are left. So I will be able to solve one more question. Shall I? Okay. Since somebody has said yes, let me go for that. One more question we will solve. Okay. 3 charges, negative Q, capital Q, and negative Q are placed at equal distances on a straight line. If the potential energy of the system of these charges is 0, then what is the ratio of Q is to Q? We have a system of 3 charges. You have, and the potential energy of the system of these charges is 0, then what is the ratio of Q to capital Q to small q? So what is, how do you find the potential energy of a system of 2 charges? Here we have negative Q. This is positive Q. This one is negative Q. At equal distances. This distance is R. This distance is also R. If the potential energy of the system of these charges is 0, then what is the ratio of Q? You should find the ratio of capital Q to small q. So how do you find it? You can find the potential energy of the system of these charges. First, 1 by 4 pi epsilon 0 q. This one is brought. For that, we should not do any work. And the second one is brought. So we have to do some work. So to bring the, remember that, to bring the negative q first, no need to do any work. So the work done for bringing negative q is equal to 0. Then I am bringing the positive q. So work done will be 1 by 4 pi epsilon 0 q into negative q divided by r plus. What about when you bring this negative q? What will be the work done to bring this negative q now? That will be equal to 1 by 4 pi epsilon 0 into negative q into negative q divided by what is the distance of this negative q from negative q? This is r, this is r. So divided by 2r plus, again, you have to do work against this capital Q. What it will be? 1 by 4 pi epsilon 0 into capital Q into small q divided by, what is the distance between these two? R. Is it clear? So first charge is brought, work done is 0. Second charge, capital Q is brought, work done is 1 by 4 pi epsilon 0, negative Q into positive Q by R. Distance between them is R. Now the third one is brought. So we have to do work against the potentials due to negative Q and positive Q. So against negative Q will be 1 by 4 pi epsilon 0 negative Q into negative Q divided by this total distance 2R. And this is equal to 1 by 4 pi epsilon 0 into Q into negative Q by R. So this sum should be 0. So all these three together should give 0. Now we can cancel some terms. 1 by 4 pi epsilon 0 is common everywhere. This is negative Q into Q, negative Q by R, plus this is negative Q into negative Q, that is Q square by 2R, plus capital Q into small q by R, that is also equal to 0. The sum will be 0. So when Q is common in both three equations, small q is common there. So it will be capital Q by R plus Q by 2R. Is it plus? Sorry, I made a mistake. Negative Q. This is positive, and here it is negative again. Q into negative Q. Sorry, the sign is negative. Negative Q. This negative also I missed. Negative Q by R is equal to 0. From this, you will be easily able to find the ratio of small q to capital Q or capital Q to small q. So let me check it. Negative Q into Q by R. 1 by 4 pi epsilon 0 is cancelled. So negative Q into positive Q by R. Here it is negative Q into negative Q. So Q square by 2R minus Q into Q by R. Okay. Then one Q is cancelled everywhere. So this Q has gone. This Q square has gone. This Q is gone. I am dividing the entire equation with Q. So we have negative capital Q by R plus Q by 2R minus Q by R. We have two negative Q by R's. So they will be adding together to give negative 2Q divided by R. Am I right? Negative Q by R plus negative Q by R. That is negative 2Q by R. This will be 0. So what you will get, Q by 2R is equal to 2Q by R. So we can find the ratio. This again, these two R's we can cancel. So what you will get, small q by 2 is equal to 2Q. That shows small q is equal to 4Q. So what is Q by small q? Q by small q. What it is? Q, capital Q by small q. This 4 will come here. It will be 1 by 4. Or this ratio is 1:4. Okay. So we should only know the equation for the energy of a system of 3 charges. So that's all about this problem. And now we got the answer as 1:4. Somebody has solved it. Very good. So we got the answer as 1:4. I got some more questions, but my allotted time is over. So I am going to sign out. Thank you very much for listening to me. Okay. All of you can leave the meet now. Thank you very much. Good night. I think all the problems suspended were okay for you. If you have any doubt in any problems, you can give the feedback. I will explain it. Okay. In case of any doubt regarding any question, you can ask.
Bye, sir. Bye. Join with Dipole now.